So previously we've looked at the transfer of heat between one object into another that has only really to do with a change in temperature. Now we're going to bring into this idea of internal energy, enthalpy, and how that relates to heat and also work within a reaction. So hopefully we'll be able to explain how our change in internal energy, capital E is internal energy, can be manifested as heat and work, and then be able to quantify the relationship between delta H, enthalpy change, and delta E, change in internal energy, as it relates to heat and work done during a reaction. So one important distinction that we have here is that we're looking at reactions. So that means we're going to break bonds, and we are going to then form bonds. And reminding ourselves, when we break bonds, that increases potential energy of those atoms because we've decreased the amount of attractions. And when we form bonds, that decreases our potential energy of those atoms as they form those new attractions. So now let's look at, as we break those bonds and form those new bonds, how does this relate back to internal energy, enthalpy, heat, and work? So what we know is that for every system, there's a specific amount of internal energy and enthalpy. And importantly, these are state functions. That reminds us, that means I could go ahead and look at that function, that property, and I can quantify that property without making it undergo a change. Now, they can undergo changes, and we call that change in internal energy and change in enthalpy. So now when we're looking at this specific system that we have here, let's go ahead and say, when we look at this, we have some system with initial conditions. So that means we have some initial internal energy, and that would be some amount of kinetic energy and some amount of potential energy, because our internal energy is the sum of all the energy in that system. Well, then we also have some system at a final internal energy and final enthalpy. So we could say there is some final, as we undergo some kind of change where we've changed possibly our kinetic energy and we've changed possibly our potential energy. So we undergo this change between our initial and our final. Now, one important thing when we're talking about our internal energy, as we're looking at this, is the sum of all the energy in that system. So this could be from bonds, this could be from molecules moving around, whatever it would be, we can undergo. We can see that we have these differences in our kinetic energy and potential energy. Now, as we undergo a change in internal energy, so let's say we undergo some kind of change that causes it to go from reactants to products, initial to final, whatever it would be, that change in energy is going to be equal to the difference between our final energy and our initial energy. So these are differences. That could be because maybe we underwent and we noticed that we saw maybe a change in our kinetic energy, or possibly we see that we have a change in potential energy, or both. We can notice that we can have both of those changes. Now those are kind of thinking, we start initial and we final. How is this energy manifested to the surroundings? So this is our reaction undergoing a change. How is it going to be manifested? And the way that we see this manifested is by the Q of that reaction or the work of that reaction. So Q would be heat, W would be work. So these are the two ways that we would see that our energy is manifested. So it's going to undergo this change. Maybe we have a change in kinetic energy, and that change in kinetic energy corresponds maybe to this amount of heat that is released or absorbed by that reaction. Or maybe we have a change in potential energy. See how maybe that connects to work. But we do notice that there's this change and it gets manifested to whatever is around it by that reaction doing work, having work done on it, the reaction releasing heat or absorbing heat as that reaction occurs. So that is this idea of internal energy. We also threw in this idea of enthalpy. And maybe let's do a quick definition of what we mean by enthalpy. So enthalpy is defined as the internal energy, and maybe let's just say this is our initial enthalpy, our initial internal energy, because we're starting with our initial system, some initial volume and pressure that we were in. So we can think of enthalpy, if we want to give it a good maybe conceptual definition, We can think of enthalpy as the total amount of energy needed to make that system. Now we think, why would that be different than possibly just our internal energy? So we do notice that our internal energy is there, but we also notice this other piece here, our pressure and our volume. Well, in order for something to occupy space, it's got to push away from and make space for that object. So we can think of, we see here that our enthalpy is not only all the internal energy, but it's also how much space and at what pressure is our system occupying in that specific condition. Maybe it's all the molecules of my reactants, maybe all the molecules within two different reactants, whatever it would be, but it's also the amount of energy needed, because we have to make, in order to make that, we have to have space or volume. It occupies somewhere within our system. Okay. Now, as our reaction undergoes some kind of change, we then get to some final enthalpy, which is our final internal energy and our final pressure and our final volume. And again, now as we notice here, we're going to change our pressure, our volume, our internal energy, which could then cause a change in our enthalpy. So now if we connect this back to our change in enthalpy is going to be our final enthalpy minus our initial enthalpy. And our change in enthalpy is going to correspond to the changes of what's inside of it. So this would be our change in internal energy plus the pressure our system occupies times the change in volume that it undergoes, because it's going to maybe expand, maybe it's going to contract, but we do notice that it's going to undergo this change. So now as we go from reactants to products, we're going to have this change in enthalpy. Now we're going to bring this back to how does that relate back to our internal energy, and then we'll correspond that to work and heat. Now I'm going to do a quick sidestep and remind us that our work and heat are non-state functions. Because we remind us this is not like delta Q or delta W. Q, or heat, only has meaning if we undergo a change. We have to have heat transferred in order for that change to occur. So it doesn't have any meaning. It's a non-state function. I cannot say the heat of my reactants is X. Likewise, work. Work only has meaning if we undergo a change. So these two here would be non-state functions. We notice that those non-state functions only have meaning if they correspond to a change of that state function. So a change of our internal energy, or possibly if we connect it back down to enthalpy in a minute. So we notice that we have a reaction that maybe has different bonds. So maybe we've changed our potential energy. Maybe we released heat or absorbed heat, so there'll be a change in kinetic energy. But those all are manifested in these non-state functions as heat and work. So if we maybe summarize this a little bit, and we come down here and we see when a system undergoes a change in conditions, so we undergo some kind of reaction, the change in internal energy can be expressed in two forms, heat and work. So that's W, and this would be heat, would be Q. So again, these are the ways that they're expressed. These are the ways that they are manifested, okay? But the reason why we release heat or do work or have work done on our system is because both of these are caused by a change in internal energy. And when we're thinking about reactions, it's all about bonds breaking and bonds forming. And that's everything to do with how they're going to then release heat, absorb heat, do work, or have work done on the system. So this gives us hopefully a good summary of this idea of heat and work, how it relates back to enthalpy and change in internal energy. But now let's go ahead and maybe make a quick summary of how do we quantify heat and work for a reaction. So when we're talking about a reaction, we're talking about what we call expansion or PV work. And that would mean that my reaction volume is going to expand, so our delta V is positive, or contract. Our delta V is negative. So we go from a larger volume to a smaller volume, or a smaller volume to a larger volume. Well, that would mean that as it does that, it's going to push out. And we think, how does this correspond back to work? If we think of, maybe this was my initial condition. Maybe we have some kind of movable piston here, and we got our reaction volume inside of here. And then now we go to a larger volume, where now my reaction is going to occupy a larger volume. So we have a initial and final condition. Well, in order for that to happen, we have to think, well, that reaction actually had to push out and do some work. So in order for it to expand, it's going to lose energy by pushing out against the surroundings. So we're going to do work by the system when we expand, or likewise the opposite would be true. If I went backwards this way, that would mean our surroundings is pushing in on the reaction and causing it to get smaller, and the reaction gains energy. We can think of this maybe like a spring. A spring expands out, it loses its potential energy. A spring contracts in, it gains more potential energy. It's the same idea here. Well, how are we going to quantify this or conceptualize it? Is we can say work, and this is the work for the reaction, is equal to negative P delta V of our reaction. So if our delta V is positive, that would mean work is negative. Right? It's going to lose energy as it expands, because this is the pressure, not the change in pressure. This is the actual pressure. We can't have a negative pressure. Well, or if we had a negative delta V, again, our pressure is always positive. That would mean we have a positive work, or we're gaining energy as we're being contracted from the surroundings. So this is, again, a reaction expanding or contracting, and how we think about it with regards to PV or expansion work. Then we connect this over to the heat of a reaction. Now, when we're looking at the heat of a reaction, we're going to think about, how do we actually measure heat? So let's do a quick sidestep and say, we know the Q of an object is equal to either C delta T, or the Q of that object is equal to mass specific heat delta T. Now, one important observation to make here as we're thinking through this is that this object is not reacting because it's undergoing a temperature change. What we'll see here is it is the same before and after that temperature change. Now, what do we mean by the same? It's the same substance. So I start with water at 10 degrees Celsius, I end up with water at 50 degrees Celsius. It's not undergoing a change in what's present there, the substance that's present there. So then, how does that relate to a reaction? What we'll see here is that the Q of a reaction, again, is caused from a change in potential energy or a change in kinetic energy of that reaction. And a lot of times we think of it as a change in potential energy, and that has everything to do with our bonds breaking and forming. Well, we don't have the ability to directly quantify potential energy of our reactants and potential energy of our products. So we'll notice here, when we're looking at the Q of a reaction, we're going to indirectly quantify the Q of the reaction by observing the change in temperature of our surroundings. Now, what that means is that I can think of our surroundings as undergoing a temperature change. So I can see here, again, going back to the idea of law of conservation of energy, the Q of my reaction is going to be equal and opposite to the Q of the surroundings, so whatever is going around it. And our surroundings is the thing that's undergoing a temperature change. So now as we're looking at our surroundings undergoing this temperature change, that means we can calculate the Q of our surroundings as C delta T, or the Q of our surroundings as MCS delta T. Now, once we know information about our surroundings, we can measure temperature. Right? That's something that we have the ability to quantify and measure by using a thermometer. That gives us the ability to then backtrack and tell us some information about how much heat is released or absorbed by a reaction. And so now we see the Q of our reaction is caused by a change in potential energy, which means we don't have the ability to directly measure that. We cannot look at the potential energy of my reactants and the potential energy of my products. But what we can do is we can look at the change of that potential energy, and we can do that by looking at what is it affecting. If a reaction releases heat, the surroundings is going to absorb that heat. If a reaction absorbs energy, it's going to take it away, or it's going to be given energy by the surroundings. We'll see that these two are directly related to each other. It's really important. We'll see this when we get to quantifying heats of reaction. This is a really important idea that we want to focus on as we're looking at that heat transfer from the surroundings to the system, the reaction, or from the reaction, which is our system, to the surroundings. So now that we have that as kind of a foundation, let's go ahead and look at an application problem. So this is where I'd like for you to pause and practice. So we have our information provided, and then I want you to go ahead and pause the video and answer the questions on your own. And then come back and see how I thought through these. So I'm going to read their question. Inside of a balloon. So what does it mean for something to be inside of a balloon? That is something that is constant pressure. And so that means that my pressure is constant, but our volume can change. So we see here constant pressure, a balloon, you blow into it, you make the volume get bigger, but you're not changing its pressure. So inside of that balloon, we have baking soda, sodium bicarbonate, reacting with vinegar, acetic acid. During this reaction, we know 50 kilojoules of heat is released, and the balloon expands, in which the system does 2.5 kilojoules of work. Now I want you to go ahead and pause the video and answer these questions A through D. All right, so now that as you had a chance to look at these, let's kind of maybe think through some of these questions together. Now, I'm going to start by just making sure we can see what information can we extract from what we are given. So we know that 50 kilojoules of heat is released, meaning the Q of our reaction, because we're releasing heat from this reaction, if we release it, that means it's negative 50 kilojoules. That reaction gave away 50 kilojoules of heat. The balloon expands, so we think of work equals negative P delta V. It expands, so our volume is positive, which would mean our work should be negative. We should be losing energy as our balloon expands, the reaction. Remember, this is the work of the reaction. And the system, or our reaction, does work. When we say something does work, you're losing energy when you do work. So that would mean, again, going back to conceptually what we just identified here, our work is negative 2.5 kilojoules. So a couple of observations to make. Number one, we notice that both of these are releasing energy. Number two is that our Q is much larger than work. And this is an observation that we make, we'll notice a lot, is that our work value is many times much more smaller than the heat that we would see for a reaction that we would have. So now that we have that kind of in our wheelhouse as we're thinking through this, let's answer some questions. So maybe let's do B first. So what is the change in internal energy of our system? Well, we know that the change in internal energy is either our final minus our initial internal energies, but we don't know anything about that, right? We didn't quantify our initial internal energy. We didn't quantify our final internal energy. But we do know that those are manifested in two forms, the Q of the reaction and the work for the reaction. So we can say that delta E, and I'll be maybe really specific here, for our reaction is Q, which we just said is negative 50 kilojoules, plus work, which is negative 2.5 kilojoules. So we could go ahead and we could say the delta E of our reaction is negative 52.5 kilojoules. So we see here that when we undergo this reaction, we're releasing energy both in the form of heat and in the form of work. So now let's maybe jump back to enthalpy change. We said our enthalpy change is equal to our change in internal energy minus plus pressure times our change in volume. And we go back here and we look, well, that looks a lot similar to P delta V. Well, if we go ahead and make this negative W, well, that's going to be equal to positive P delta dV, right? We multiply both sides by -1. Well, what we see here is that that's the same as what we have right here. So if we go ahead and let's maybe put in work here, because maybe that'll tell us something. We didn't measure our pressure or change in volume. So we see our delta H is going to be equal to our delta E, and this would be minus work. Now let's do one last step. And we know our delta E is equal to Q plus work. So let's go ahead and plug that in there. So Q plus work, that's our delta E. And we also see that that is minus work. Well, hopefully we can make this observation and notice our works cancel. And what we'll see here is the enthalpy change is equal to the Q of our reaction. This is one big important aspect that we'll notice when we're looking at a reaction. And this is a lot of times when we say the change in enthalpy, we also call it the heat of the reaction, because it's the amount of heat released or absorbed when a reaction is occurring. So now we don't have to do any math here, and we could say our delta H is negative 50 kilojoules, right? That was equal to our heat of the reaction. So now let's go back and answer question C. If this reaction occurred in a rigid container, so volume cannot change, the delta E of the reaction would be greater than, less than, or equal to the delta A of the reaction occurring inside of our balloon. And we want to think here, what is the same between these two conditions? Okay, our two conditions, constant pressure, that's our balloon. And we compare that to our constant volume, and that is where we have this rigid container. Well, constant pressure and a constant balloon, what we'll see here is that they are going to have, let's think about what's the same. Well, we have the same reactants, so we haven't changed what our reactants and products are. Now, if that's the same reactants, what we have here is, and we notice the only difference is that we have different reaction conditions. Well, here we would have our delta V is positive. We expand it out. And we see here with our constant volume situation, we have our delta V is 0. There's no way that it can undergo a volume change. Well, if our delta V is 0, but we have the same reactants, that would mean our delta E is constant. Now, why would we think that our delta E is constant between these two conditions? The reason for that, actually, let's not call it constant. We'll say our delta E is the same for both conditions, and that is because our delta E is dependent on our reactants and our products. So what we start with, what we end up with, right? Our initial internal energy and our final internal energy. Well, now because of that, what we'd see is that, well, our delta E doesn't change because we haven't changed anything about our reactants and we haven't changed anything about our products. We've only changed the condition. So that would mean our delta E would be the same. Now, as a consequence of this, let's think back to D. If this reaction occurred in a rigid container, again, constant V equals 0, delta V equals positive. So again, if we're at constant pressure or we're at constant volume, we look at these two conditions. We just said our delta E is the same, negative 52.5 kilojoules. Our delta E at constant volume situation, negative 52.5 kilojoules. Well, since the delta E is the same, because again, they are the same reactants and the same products, we remind ourselves that that delta E is expressed as heat and work. And we notice this from our original calculations, this was negative 50 kilojoules and negative 2.5 kilojoules for heat and work. Well, what would differ between that and our constant volume situation? Well, we said our delta V is 0, and we know work is negative P delta V. Well, delta V is 0, work is negative P times 0 or 0. We have no ability to have work be done on or by the reaction. So that would mean our delta E, as we're thinking through this, is going to be equal to Q plus work, as it always is, but our work is 0. So in this condition, our delta E is equal to Q. Well, in this case, we know our delta E is negative 52.5 kilojoules. So we'll notice, because we can't release energy in the form of work, we're going to release more heat energy, because that's the only way that we can manifest this change in internal energy. And so then if we go back to this observation of Q for a constant pressure versus a Q for a constant volume, and again, this is specific to this condition, we can notice it might be different depending on what kinds of work values we have. The Q of the reaction would be greater, actually let's make it, because we notice here, if we say greater than, we can say it's more negative than the Q of the reaction when it occurs in a balloon. And that is because there's no work done, and the only way we can manifest this change in internal energy is by heat being released in this reaction in this specific example. Now, I hope this video gave us a good understanding of energy, internal energy, enthalpy, and heat and work. In our next videos, we're going to look at how do we quantify heat of reactions in two different possible conditions. One in which we do have this constant pressure situation, and one in which we do have this constant volume situation.